So now we'll have the chance to go viral, right? All these YouTube videos are gonna I've been watching the Khan Academy videos. They're actually pretty good. The guy with the colored pencil, and he shows you how he's working the problems in real time. It's a pretty good primer. What's that?
Khan Academy is what helped me pass math.
Yeah, that was a good one. And even, it's a good refresher too. You can kind of go back in and I like the way that different things are indexed too. Just go right exactly to the topic you want. It's pretty handy. So anyway, I'm just going to solve the problem Tim went through in a slightly different format. And I wrote this up already for the NRG 101 class. This is a slightly simpler version. I think what we'll find though, at the end, we're just going to take this number and, well, he had a, for 102, he made you calculate this number, 11 million kilowatt hours per year. So that was a given, but based on what you saw previously, number of hours per year, coefficient of performance of 25% and 5 megawatts, I think you can all pretty clearly see how to get to that number of kilowatt hours in a year. So let me just show you this method. And right off the bat, so going back to what Tim had, you know that what you're trying to solve for is n, just the number of turbines. And like any math problem, all the stuff you do know is on the right-hand side, all the stuff you don't know is on the left-hand side. So I just went ahead and stuck n on the left-hand side. That's what I don't know. I need to know n. I need to know how many turbines. I also knew that I need to get to 137.3 exajoules. So I know that, and then there's only two places for that number to go, either in the numerator or the denominator. And so you kind of think out loud to yourself, well, if that number got bigger, am I going to need more turbines or fewer turbines? Well, I'm going to need more. So it's got to go in the numerator. When the numerator goes up, so does the answer. Right, so there it is. I took the 137.3, stuck it right in the numerator, and I just left nothing beneath it. I guess if I were going to be a little more complete, I would just put the number 1 beneath it, right, so just to be complete. And then I went into the textbook, and I think in the back of the book, I know it's the case for your 101 text, but if we go into the 102 text, yeah, thanks. So page 528, we've got conversions from all the different powers of 10. We can see that an exajoule is 10 to the 18th, and we can see that a megajoule is 10 to the 6th. So we can do that. A megajoule is 10 to the 6th. Yeah, so I'll write that out like so. So I've got 1 exajoule equals 10 to the 18th joules, right? That's right in there. 1 megajoule equals 10 to the 6th joules. So sorry, what 0 looks like a 6?
Right there by your 10.
Oh, this guy, I'm sorry, yeah, 10.
No, below it.
Yes, it does. It looks exactly like a 6, thanks. So from that, I know that if I'm going to need 10 to the 12th megajoules to make 1 exajoule. So that's what this is, 10 to the 12th megajoules in 1 exajoule. So this number is really just the number 1. I mean, really all I did, it might sound kind of silly, but I just multiplied 137.3 exajoules by the number 1, and then I multiplied it by the number 1 again, because if we take a look on page, 529, I can see that 1 megajoule is 0.2778 kilowatt hours. There it is right there. So I just multiplied by 1 twice. And the reason for doing so is that I can just cancel the units. Cancel the units. And then finally, I know that I'm trying to get to this number N, whatever the number N is, and I know, I'm going to erase that little tiny bit there. So that's on the screen. Okay. So, and there's a couple different ways to think about that. One way is just to simply look at the units and see that, well, kilowatt hours is sitting right here. Gosh, I keep tapping my pen. Kilowatt hours is sitting right here in the numerator, and I know I'm going to need kilowatt hours in the denominator somewhere. The other way to think about it is just to think out loud and say, well, gosh, what if I had just a 1 kilowatt wind turbine, like the one sitting back in the bullpen, right? If I had a 1 sitting over here in the denominator, what's that going to do to my answer? It's going to make it go up or down?
You have 1 in the denominator?
Just, yeah, a 1 in the denominator. It means I'm going to need a heck of a lot more wind turbines. So the smaller the rating on the turbine, the greater the number. So right there, I can say, oh, I'm going to put however powerful that turbine is in the denominator, the bigger that power rating gets, the fewer I'm going to need. So there's a couple different, so you can double check in 2 ways. One is make sure the units cancel, pretty surefire way, but then also just think of it from a practical matter. If the turbine's bigger, I'm going to need fewer turbines, so therefore that power rating belongs in the denominator. Another important thing to think about on almost every one of these problems is we're actually solving 3 problems in parallel. So the first problem we're solving is just numbers and arithmetic. And there's, your 137, your 10 to the 12, your 0.2778, and your 11 million. And that's just arithmetic, just multiplication and division. So you got to keep track of that. The other problem that we're solving simultaneously, and as I said, in parallel, are keeping track of the powers, both in a numeric format or in a powers of 10 format. So here's your mega, here's your exa, kilo, et cetera, et cetera. And obviously, what we did right here, we traded. You can trade an M for a 10 to the 6th. You can trade an E for 10 to the 18th, but you're keeping track of that as well. So you're keeping track of just the numbers. You're keeping track of the powers through these powers of 10 prefixes. And then the third problem you're solving in parallel is keeping track of the units. So that's kind of the slight jump away from conventional algebra. Like in conventional algebra, you've got the numbers and you've got the symbols. And that's the equivalent of sort of problem 1 and 3. But maybe it's that middle part that can sometimes be tricky. You say, well, I'm going to throw an M on it. It's there to make it easier, so you don't have to deal with such large numbers, obviously. But that's really a good way to look at this. You're actually solving 3 problems in parallel. Does that make sense? Kind of a different way of looking at it than how. And like I said, the way Tim solved it, the way I solved it, they're both right. Neither one's wrong. It's just a matter of convention and what you're into. I will say, for the way I solved it, it's all sitting right there in front of you, and if you make a mistake, you can go back and just sort of erase that one mistake and not have to go back to the whole problem again. In the method Tim went through, gosh, you could have made a mistake on page 1, and it just kind of propagated, you didn't realize it. And in fact, we saw one little example here. Did he actually make an error, or is it just?
No, it's because it's megawatts on top and kilowatts per year.
Oh, I got you. Here's the M. Okay. Yeah. So that's an example of keeping track of that second track of the 3-track problem. Okay. And I'm not gonna say that's as tough, well, that's about as tough as the math is gonna get in 102. You know, we're not gonna do a bunch of trig. We'll look at a little bit of calculus in here. I'm not gonna expect you to solve calculus problems, but I am gonna expose you to some of the calculus jargon. In fact, I think the Solomon paper has an integral sign in it, so we're already taking a look at some of that. Okay. So, we'll just take a Camtasia break.